Sufficiently creative use of bits has gotten us very large integer values in base 2. Now let's look at something that's not numerical. Text symbols, like the letters A, B, and C. Clearly we want to store text in computer memory, documents, people's names, emails, and so forth. How do we do that? Well, as you can see in the diagram, we can store Roman alphabet letters, standard English letters like A through Z, by assigning a numerical value for each letter. So in our example, we see a 1-byte binary value, 65. That's a 1 in the 64's place and a 1 in the 1's place. And we'll say that 65 stands for capital A. And make 66 stand for capital B, and 67 for capital C, and so on. We'll assign a unique numerical value to each letter from A to Z. Now, this is not a completely unfamiliar idea, really, if you think about Morse code, which you may have encountered at some point. It represents each letter with a series of dots and dashes, in effect ones and zeros. And we're doing the same kind of thing here, giving each letter a particular 8-bit 1 and 0 pattern. If we agree that a certain area of memory is meant to store text, we can store 1 letter per byte using this numerical system. So a 1,000 character email, for instance, would be stored in 1,000 bytes, with each byte holding the number code for one of the characters. It may seem an odd choice to use 65 for capital A, but it turns out that the standard system for assigning numbers to letters does this. It's called ASCII code, and it's used in just about every program in one way or another, possibly as part of a more modern code that we'll see in a minute. ASCII stands for American Standard Code for Information Interchange, but you don't have to remember that. Just remember the term ASCII in capitals because it's an acronym. ASCII code does use 65 for A, 66 for B, and so forth, but it also has a different set of numbers for the lowercase letters, starting with 97 for lowercase a and 98 for lowercase b, for instance. ASCII even has numerical codes for symbols you might not think of. For instance, there's a code for each punctuation symbol, $, pound sign, percent, and so forth. Even a blank space counts as a symbol, quote unquote, and it has an ASCII code, number 32 in fact. Now you don't have to remember the actual numbers, just the principle that by assigning numbers to symbols, we can represent letters as well as many other symbols such as punctuation and spaces. And a question for you. Look up the full ASCII table online, you can get it easily, and translate this sequence of ASCII values into its textual equivalent. So if you've had a chance to do that, you should have found that a 72 is an H, a 101 is an E, 108 is an L, lowercase, and 111 is a 0, so it in fact says hello. Now there are a total of 128 different ASCII codes, going from 0 to 127. So 128 symbols may be represented by the ASCII system. And this is sufficient to express anything you would type in English. The American in the name for the code reflects a bias. Back in the day that ASCII was created in the early 1960s, this seemed sufficient. But of course, limiting the system to English text alone today is pretty narrow. So there's a newer symbol coding system that is displacing ASCII. And this system is called Unicode. And it includes a much wider variety of symbols. Like ASCII, it uses a numerical value for each symbol, but it has no limit on the values. The original 128 ASCII code numbers are included in the Unicode system as the first 128 values, but all values above that are for other symbols, representing just about every form of writing on the planet. For example, here's Unicode 20,320. It represents the Chinese ideographic symbol Ni, and the next one, 22909, is the Unicode for the Chinese ideographic Hao. The two together are Ni Hao, the standard Mandarin hello. Unicode symbols typically take 2 bytes each to store, which allows values up to 65,535. There are Unicode symbols with higher values, but they're less commonly used. In our assembly programs, we'll use ASCII, somewhat unfortunately, since assembly generally uses the older system. However, if you're learning a newer language like Java or Python, C#, then Unicode is wired in. Another topic then, some of what we'll study in assembly code will require understanding how binary numbers are added and subtracted. So let's start with binary addition, leaving subtraction for a later discussion. It's easiest to understand binary addition by analogy from base 10 addition. So at the risk of sounding silly, let's recall a few details of how that works. When we add two multi-digit base 10 numbers like the two here, we add pairs of digits, of course, from right to left. And if we get a value greater than 9 in any particular pair, 4 and 1 is 5, but 8 and 7 is 15, then we represent 10 of that total by carrying a 1 into the next position, and we leave the remainder of the value of the sum in the current place, of course. So the 5 goes here, and a 1 is carried into the next spot. After the rightmost digit pair, we add digit pairs plus any carry. So, for instance, the 2 and the 8 will add the carry, and that'll make us a total of 11. And there again, we'll have a 1 and carry 1 to the next position for our final sum. Adding 1 to a series of 9s, like 999 plus 1, results in a ripple of carries, with each place getting set back to 0 and a 1 carried into the next place, which in turn gets reset to 0 and so forth. So let's translate that instead into binary. Binary addition works in the same way, except that each digit is a 0 or a 1, of course, and carries happen a lot more frequently. Instead of carrying when the result is greater than 9, we carry when the result is greater than 1. If both digits are 1, then a result of 2, or 1-0 in binary, results in a 0 value for the sum digit and a carry of 1. Translating the 5 rules from above into binary form, first we add pairs of digits from right to left. So let's do that for the first couple of digits here. A 1 and a 0 is just a 1, and a 0 and a 1 is likewise a 1. But the next pair is a little more interesting. If we get a value greater than 1, 1 plus 1 is 2 here, in any digit pair, then we represent 2 of that total by carrying 1 to the next position, and we leave the remainder of the value of that sum in the current place. So if the sum is 2, then we leave a 0 here and a carry of 1 into the next position here. And this position will again end up with 2, a carry of 1 plus a 1 in the upper number, and so we'll once again have a total of 0 and a carry of 1 into the next position. Now for this one we have a carry and a 1 because we're adding, we have a carry and 2 1s, so the total is 3. And in that event, 1, 1 in binary would be 3. We carry the 1 to cover 2 of that value and leave the remaining 1 in the position here to have a total of 3. So there's 1 here plus a carry of 1 into the next column up. And it happens again here, right? So once again we'll have a 1 down here and a carry of 1. In the 0 and 0 column we will have only a total of 1 because of the carry, and in the final column again a value of 0 and a carry of 1. You can have one more digit actually resulting from a carry out of the topmost bits, although typically that gets dropped when we do addition in the computer. Notice that no matter what, the carry value will never be greater than 1, because the worst case of adding 1 plus a carry, we still get just 3. Now, adding 1 to a series of 1s, so if I took 1, 1, 1 and added 1 to it, results in a ripple of carries, just like adding 1 to 999 would in the case of base 10. So each place will get set back to 0. Here we'll have, for instance, a 0 but a carry of 1, and then I'll fill in the missing zeros here to make this maybe a little clearer. And when we carry in the next place, we'll end up again with a 0 and a carry of 1 into the next spot, and once again a 0 and a carry of 1, and finally here in the fourth spot we get a 1. So the 1, 1, 1 rippled over to 1, 0, 0, 0. And probably no surprise that I'll ask you to do an in-lecture question. Please add the 2 binary values shown here by the red arrow and get the result, and also how many times do you have to carry when you do that addition. So the result is a 11001000, and we have to carry 6 times. Let me kind of just draw that out for you here. the first two digits, 1 and 1, added 2, and that's a 0, and a carry of 1. So with our carry of 1 over here, we now have a 1 plus 1 and 0, again a 2, so a 0 and a carry of 1. We're getting that ripple effect here by adding 1 to 1, 1, 1. And the third carry occurs in the third column as well, and we wind up with a carry into the fourth with 0 and 0 and 1, and finally no carry out of that column. When we add the 1 and 1 in the next column, that again is 2 with a 0 in this column and a carry of 1 to the next. It's a fourth carry. And then 1, 0, 1 gets me 2 again. 0 here and a carry 1 into the next. That's the fifth carry. And 1, 1, 1 gets me 3, 1, and then a carry, the sixth one, into the final column. And there's the result. And then a third in-lecture question. Assuming we have a carry of 1 from the prior place value, let's call that a carry in, then what combination of bits in the present place will cause a carry into the next position to the left, a carry out? If you stop and think about that, then any combination of bits other than 0, 0 results in a carry out if you have a carry in. Even a combination of 0, 1 plus the carry in results in 2, and that causes a carry out.